Hello and welcome to Module 2 of our class. I am very excited to go through this lecture. It's probably one of my favorites because it's all about visualizing data and creating insight from tabular methods. So from last class, we talked about how data can be started to use as information, and it's been great to see all of the comments and troubleshooting and collaboration that's going on in Slack. So I definitely encourage you to continue providing each other with help. And as you challenge yourself and go through, you are learning a lot. So I'm really happy to see that, and feel free to continue answering each other's questions. And I'm usually not one to try to give you the answer. I would rather give hints and help you come to the solution yourself, and really just keep up the good work. So for today, let's dive in to the lecture. I will share my screen. All right, let's get started. In this chapter, we will construct a frequency distribution for different categorical variables. This will build off what we covered last week when we talked about different types of data. And this helps to visualize the proportions of each category. And we'll use bar charts and pie charts, and we'll talk about what makes a good graph, what makes a bad one. And we'll look into the relationship between categorical variables by constructing contingency tables and stacked bar charts. We'll also analyze numerical data by looking at frequency distributions, scatter plots, and histograms. We will also touch upon some important considerations when creating data visualizations. So first, I always like to start, why is this important? Why is data visualization sometimes called data viz? Why do we need any of this? So the saying, a picture is worth 1,000 words, but why is that? Probably because information in tables or in raw form is very difficult for people to easily interpret. Computers understand data as numbers, but people do not. And data visualization helps bring structure to data that helps us create information from raw data points. And we visualize to communicate and explore. When we are presented with a categorical variable, it is often thought to summarize the distribution of each observation for the different categories. The relative frequency for each category equals the proportion of observations for the category. And let's use the example from the textbook that looks at the Myers-Briggs assessment, which is pretty much just a personality type of test, maybe a silly example, but it looks at 1,000 different employees and wants to assess the different personality traits, perhaps for different team building purposes. So the variable that we're looking at dictates a label for each employee. There is no nominal scale. First, let's convert this into a frequency distribution to see how often each category came up. We divide by the number of observations, or N is usually a variable we would use to state the total sample. And this is what we use to see the relative frequency when we divide by the total population. We can bring this to a percentage by multiplying it by 100, and the proportions will all add up to 1. So if you take something and divide it by the total, all those different proportions will then equal the total amount. And then this leads us to be able to now compare between the relative frequencies. So we can say 40% of the employees are labeled as explorers. But if we wanted to quickly see how does that compare against the other categories, just using this table on its own, it'd be difficult to really interpret the key differences. So let's visualize this as a bar chart. And here is what that would look like with the relative frequency of each category. And the height of the bar represents the frequency. And so we can see easily that the Explorer is the highest, with Diplomat close behind. Then Sentinel and Analyst are similar, but we really intuitively can observe that Sentinel is higher. And this I'm always someone who promotes just keep it simple. It's always, you want graphs. We'll get more into this when we talk about visualizations that are good examples and things that are sometimes a pitfall. But on the right is one example of a pie chart. And if you could take one thing away from my class, and if it's not to ever use a pie chart again, I would consider that a success. So let's talk about it and why it's actually difficult as a visualization tool to really understand some of these differences. So this is the same exact data, now just visualized in a different way using a pie chart. And we see the proportions are cut out of the whole. So it helps us visualize that all of these together equal 100, and each slice is relative to the frequency that it shows up. And I would argue, and others do too, that it's actually really difficult to intuitively see the difference between Explorer and Diplomat without actually reading the percent number, which defeats the purpose of having a visualization if you're going to need to rely on the number anyway. And that's also, there's some reasons behind that. I added an article that talks about it, but it's really hard for the human eye to understand and interpret these angles as being different things. And later in this lesson, we'll discuss, again, what makes a good and a bad visualization, but pie charts are a big pet peeve of most data scientists. Let's move forward. When we want to look at more than one categorical variable, we can use contingency tables to see the relationship between two variables. Additionally, we can visualize it using a stacked bar charts and colors. Just making sure my screen can be seen. Let's use the same example about employee personality tests, and now we can add the variable of gender or sex, and we can use a contingency table to show that personality type is more prevalent between male and female employees. So if you wanted to now compare between different demographics, we can now start to do that. And we see the mutually exclusive combination of each pair of variables. And to bring this into a chart is now more easily to interpret. And we can use this stacked bar chart. So now we're slicing and dicing some of the data similar to what we did last week, and now visualizing it. So if someone wanted to know how are these things different, we can see it using this stacked bar chart. We break up each segment into the distribution of male to female and use the legend to show the values. And so from this, we can see that for each category, there is roughly the same number of male to female. Next, we will move on to visualizing numerical values, which is when the data represents a meaningful count or amount. We use the same frequency distribution approach from the categorical data, but this time we look at the stacked bar chart as continuous values. This is the main difference between categorical and numerical data. And for categorical, we have these well-defined intervals that are nice, clearly cut bins. But for numerical, we can bin our data into intervals. Since it's a continuous line of numbers, we create these types of bins using a range. These intervals should be mutually exclusive and exhaustive to provide that total range of data that use the same type of categorical representations. Intervals should be easy to recognize and interpret, and generally the width between intervals should be constant. If you ever spot some data visualizations where they're actually trying to skew some information, or sometimes the human eye doesn't recognize that the intervals are different because that's just not intuitive, but sometimes things can be skewed when you change the interval size. So that's why it's important to be consistent and not try to distribute the data based off of those intervals, but we'll get a little bit more into that. So the width between intervals should be constant is really what I'm trying to get at here. And we can use a rule of thumb to take the maximum value and subtract it by the minimum, divide by the number of intervals we want. So kind of, counting by fives, counting by tens. There's no right answer, but really what makes more sense as a reader of this graph. So using the example case study about house prices, we'll construct a frequency distribution, and that's what you see here on the right. So we define the intervals in this case. We will count by hundreds and cut the price data using this interval. Then we can see how the frequency distribution looks like. And this allows us to now intuitively see that most of the houses are in the range of $200,000 to $300,000. And the rest of the houses are close to this value, with a right tail of only one home that is between $600,000 to $700,000. We can also think about frequency as a cumulative pattern, where we can better represent how many houses sell less than a certain value, such as $200,000. We can add together in a cumulative way for each range to find these frequencies. And Python has some handy ways to visualize cumulative frequencies, which we'll get into the demo after the slides. And we can visualize on a cumulative basis that 80% of all home values are less than 400,000 and see the relative growth plateaus after that. And notice that we reach 100% when we are at the end of all frequencies. And this makes sense because now the cumulative of all of them will equal the sum of everything. So there's no more to add once we reach all the values. Rather than breaking the data into discrete bins, which can add arbitrary decision, a little bit of what I mentioned before. And I recently saw a graph where it was about COVID rates, and there was a percentage at the top that was different. And I can share that on Slack because I was like, this happens all the time. So when we add arbitrary decision to how to interpret data, again, this is imploring your own bias onto the insight that can be taken from the graph. But anyway, we can leverage the continuous nature of numerical values and construct a histogram. And histograms are interpreted in the same way as bar charts, but there's no gap between the interval limits. So we don't need to define those ranges to say between X dollars for each bin. This is just the continuous spectrum. What is the frequency for each continuous value? And this gets more into proportions of the area rather than a discrete count because there is no interval bins. So we think about area under this column to understand the frequency of how often this value occurs. So for our home price example, this is what the distribution looks like as a histogram. Now we can see more granularity in the information and can see more that around $250,000 is where most of the houses are in the price range. So when we distill the data in different ways, we'll get slightly different insight. And notice how we can see more detail in the overall distribution of values. Next, we will talk about line plots. And the textbook calls them polygons, but I haven't really heard that too often in the industry. But anyway, that's what we're talking about here. Similar to the bar chart, we plot the interval frequency as a point and then connect the neighboring points with a straight line. This helps to see the downsloping trend in the data. And we see the data is positively skewed, with most of the houses within the $200,000 to $300,000 range. So similar insight, visualizing it in a slightly different way. We can also visualize the cumulative price range using the line plot, where the textbook calls this an ogive. We see a similar pattern from the bar chart, but the smooth curve helps to visualize the plateau a bit more clearly. Next, we will look at scatter plots, which are used to visualize the relationship between two variables. When looking to see how something like height of parents might relate to the height of their offspring, we put the independent variable on the X or horizontal axis, which in this case would be the height of the parents, and the dependent variable on the Y axis or the vertical axis. And this is important to know which is the independent, which is the dependent. And the independent is like the word independent, nothing else depends on it, like the parent's height, where a child's height depends on the parent's height. Or at least this is what we're looking into for this type of case study. And this allows us to quickly see any patterns between the two variables. Scatter plots are just the visual representation of how all the observations look, and we usually fit a line to show the general slope of how this relationship works. And we'll get into regression lines pretty much at the end of the semester, but for now, think of it as a line that represents the general direction of the data. And from this example scatter plot, we see that there's a positive linear relationship between the height of fathers and the height of their sons. Other relationships could appear when visualizing a scatter plot. A linear relationship exists when there is a one-to-one relationship between the variables, such as when X goes up, Y goes up, or vice versa. The relationship might also not be a straight line all the time. It might not be one-to-one, such as we see in the middle here, B. This is more of like a non-linear relationship because a curved line would best fit the data. So different patterns in the world will follow different kind of linear and non-linear patterns. Something nonlinear could be exponential, a quadratic relationship, such as the total production curve from economic growth. This will look into employment and total output as the dependent variable. There also could be no relationship between the data points. This would look something like a horizontal line, or really just like a random scatter plot of noise of data points. And there would be no apparent relationship or pattern we can infer. And that would perhaps imply that there is no direct relationship between your independent and dependent variables. Let's consider the following example from our selling price of houses data. What if we wanted to analyze how to optimize renovations for houses to increase the total selling price? We want to know what exactly should we do to really bump up the price of this real estate, because there's lots of different things you can do to improve a house for that type of investment purpose. And we might consider adding a bathroom, adding a bedroom, or increasing the square footage of the house. We can visualize the relationship between price and these variables by building a scatter plot. This way, we can strategically renovate a house to get the most mileage for the dollar. Here is a scatter plot of square footage against price. And notice that the x-axis has the independent variable of square footage, and the y-axis is dependent on square footage, which is price. So the more square footage you have, we see that the price goes up, which again makes intuitive sense. We will plot this line of best fit, which gives us that information of saying the trend is positive. And this is essentially using the slope of y equals mx plus b to just capture that general linear pattern of the data. And we'll get more into this towards the end of the semester. We can use other elements of a graph, such as color or shape, to represent categorical variables. And this gives us a new lens into the information we're already looking at. We see a positive linear relationship. I don't have the line on there, but your eye can kind of see that the higher the square footage, the increase in price still. And now we see the difference between a condo or a single family house. And we can now see that condos tend to sell for less, even if they are on the higher square footage side compared to single family houses. Now that we reviewed some fundamental graph types, I want to get back to the question of why visualize. We will use this case study of Anscombe's quartet to show why. And this case study I think is really interesting. It's also from Professor Bianco's class. And this quartet comprises 4 different data sets that have nearly identical simple descriptive statistics, which we talked about in the last class, such as the mean, but also something like standard deviation, which we'll get more into explaining what that means. But pretty much these data points, if you look at just the average and how the variance is using a simple descriptive statistic like mean or standard deviation, they're exactly the same. But we'll see what happens when we graph them and really see what these data points are saying. So here you see the data for each group of 11 points. In orange shows one distribution of points as the first quartet. And let's look in Python to investigate how these distributions are different. So I have that screen over here. All right, so we'll get into this after the slides, but I'm just going to load in the packages I already have here. So we can start using some of these things. Notice I have to hit run to make sure all my packages are loaded. And I'm just going to go to this demo of why visualize using Anscombe's quartet. And again, this code is from Professor Bianco, so I give reference, and you can see her notebook that she has here, but I just took some of the key points. So we read in this data, and this is what it looks like. I'm not going to get too much into how we clean the data because you see it's a little bit unruly here. We got to get it into a shape that we can now work with. But really, I just want to show how it's kind of interesting to see how data that looks like this, if you look at a table, there's no way to really know how are these different distributions different between group 1, 2, 3, and 4. So let's just read what is the mean and standard deviation of all these different groups. And as I mentioned before, they all have the same exact mean, the same exact standard deviation. So you might say, these are all just very similar data sets. But let's visualize them first using box plots and then histograms. And later in this lecture, we'll talk a little bit more about these things. But for now, I just wanted to show you why we would use it. And we see the box plot shows the distribution across values of the information itself. So we see in this distribution, the tails are a little bit longer, where we have values that go from 4 to 11. This distribution we see similar to 4, but it goes not as far. And we see the main bulk of the information in this box, which the middle green line shows the median value. And we also can spot some outliers using the box plot, where we have different points here that we didn't actually see in one. So this is a little bit of a foresight into how we would start to see this data outside of it. But this kind of still doesn't tell us enough information about how are these different samples different from each other, because these two look pretty similar. So let's start to look at what the histogram would show. And this now shows us the distribution across the continuous spectrum. So now we actually are starting to get a little bit more insight of what the data might look like underlying the tabular format. We see this is generally centered around the mean of the middle. This one, the mean is slightly to the left of the majority of values. And these two, again, have kind of similar distributions, just judging off the shape. And even though they all have the same exact mean of this value, we can now start to see the distribution of data around the mean is actually very different. And this gets into, I don't need to get into the details too much, but feel free to read through it. This is just fitting a line of the regression. So we'll get into this later in the semester, but this is really helpful to then visualize what that line looks like across the data points. And this is really the aha moment when we start to plot it as a scatter plot, where we see now the distributions are very different, even though they had the same exact mean and standard deviation, where we fit a line on this one, which kind of looked like our price data set from the houses, where we see this positive relationship. But in this one, it's actually a lot more of a nonlinear relationship, where we see a very different pattern in the data compared to 3 and 4, which had these similar outliers, which actually made the mean very different. And we see these points are actually kind of, these two are a little more similar. And then this 1 and 4 looks very different from all the rest. So we see the actual data is very different between the distributions. And that's the point of that little case study of why do we need to visualize. Now getting into some other aspects of what makes a bad visualization. I talked a little bit when I was talking about pie charts, but now I'm going to put pen to paper and say, like, why is that not considered a good data viz and not just my own pet peeves for what we work with. So what makes a bad visualization? In a general sense, anytime there's ambiguity, distortion, it's misleading, or there's a distraction. Going back to our Occam's razor principle, sometimes less moving parts makes a better graph. So let's talk first about ambiguity. So what are some things that are wrong with this plot? If this was not a recorded class, I would ask you and I would try to hear what everyone had to say. But for now, I'll tell you what I see. First, the title is not clear. It also looks like the order is wrong. This is T versus V, which we don't necessarily know what either of those things are plotted, but when we see it plotted, it's actually V versus T. There are no units telling me what T or V is. Also, the range on the x-axis has a lot of empty space. where most of the data is between 100 and 150, but they appear to be very clustered together. The graph should also occupy most of the data. I'm not sure why there's so much blank space in the beginning. Grid lines would have also been helpful here. And lastly, a line could have been fit to the data. I linked in the course notes to the website where this was derived from, and he has a lot of other good examples of what a more appropriate graph would have looked like. Here are a few more examples. We don't know, what is the model predicting? I don't know. It's looking to predict the dependent variable of number of votes based on the independent variable of population, but we see the legend is not clear in the first try on the left. Also, the line is not sorted, and therefore it's not meaningful. On the right, we see what sorting the data points would look like, and now the visualization is a lot more easy to interpret. So the key takeaway from this is that we need to make sure that the information itself is represented in a meaningful way. Getting back into the pie charts, if the point of a chart is to make information more easily understandable, how is this chart working for you? Let's say this pie chart represents the proportion of votes casted for 5 different candidates between 3 different points in an election they want to compare. How can you tell which candidate's doing the best? How did the race change over time? The human eye is not good at interpreting angles. Instead, I usually advocate for a tree map if you're trying to show the proportion. And this gives us now, as a rectangle, which now our eye doesn't need to understand the difference in radian angles of a circle, we can now use rectangles, which gives us a lot more feasible information just by looking at it rather than a pie chart. Even worse are 3D pie charts. Please, if you can avoid using 3 dimensions in your data visualizations, I would always say I have never seen a really good use of having 3D in most cases. Of course, there's outliers and perhaps thinking about different like data journalism, making things look aesthetic to prove a point. But really the aspect of what I want to talk about here is that we shouldn't be adding extra complexity just to have our information shown in an interesting way. Here is the same information depicted with bar charts, and now we can actually make out the differences from that last example. So I won't rant too further about 3D charts like this 3D pie chart, but just as you can see, it really is difficult to actually understand the differences, and the 3-dimension only makes that worse. Just to drive the point home, I guess I'm not done. I added a lot of slides for this. Here is a regular pie chart and how using the 3rd dimension makes it look like item C is just as big as item A, but this is simply just misleading. One last example of misleading graph, notice how, and this is from an example of journalism, notice how the y-axis is flipped, making it very difficult to interpret what is the baseline here. The use of negative space is also very difficult to know if gun deaths are falling or rising. It looks like after the stand your ground law was introduced that gun deaths fell, but they actually increased. There's no reason to have red used to fill in the negative space. It seems to almost dramatize things without really adding any information. And this graph just makes it difficult for readers to actually get the story, which is the exact opposite purpose of having visualizations. One other item I want to talk about is thinking about aesthetics versus functionality when thinking about having our information be accessible to all viewers. There is a large proportion, specifically of men that have color blindness compared to women. That's just higher. But thinking about how our visualizations, the colors we use, can actually be very difficult to interpret for someone who experiences color blindness. So there's a nice tool called Color Oracle that actually will show you on your desktop what it would look like if you experience color blindness. So we want to make sure some colors that are similar to each other, like blues and yellows, that might be hard for someone to distinguish, that we use appropriate colors so that anybody can look at this graph and be able to understand the differences. Now that we talked about bad graphs, let's talk about good graphs. And here I will reference Edward Tufte, who is pretty well renowned in his data visualization rules. And I also link to some of his work, but the representation of numbers as physically measured on the surface of the graph itself should be directly proportional to the numerical quantities represented. So this is just one rule that tones some of the other aspects that I've already talked about, where the size effect in the graphic should be proportional to the size effect in the data. So this is similar to using red that really doesn't actually align with the effect in the data. It was almost somewhat of like a artistic decision where something like this graph of fuel economy standards for autos, the different space that each line takes up is proportional to the effect of that change in the fuel economy standards. So we see this type of proportion is actually representative of the effect in the data. Another example is talking about the data ink ratio. These are kind of like high level principles that Edward Tufte developed, but I just wanted to share them with the class. So thinking about the amount of data should be proportionate to the amount of ink. We should try to keep things as simple as possible. Your information should be clear, detailed, and thorough. Labeling to defeat any graphical distortion and ambiguity. And the amount of data to label should be enough to explain the data on the graph by itself. That chart example about the gun deaths is actually a great example of chart junk, which is a term, which used excessive and unnecessary graphical effects. Any part of the graph that is not useful in providing more information should be scrutinized to reflect if the artistic style is really worth the distortion of information it creates. Show data variation, not design variation. So no chart junk. These are really just important principles when you start to see data visualizations as you're reading the paper and scrolling on Instagram. How is the information distorted through something that is aesthetically interesting? So I hope you kind of keep an eye out for some of these examples and feel free to post them on Slack. I always love seeing kind of bad graphs or just interesting when things get distorted through data visualization. So in short, the number of information carrying dimensions depicted should not exceed the number of dimensions in the data. So graphics must not quote data out of context. It's easy for the human eye to quickly compare between values. I think the Bloomberg terminal uses this often with pictorial comparisons next to the numerical data to show patterns and trends and visualize the distribution of data. If you can take advantage of the Bloomberg terminal in the Vandenberg Hall, if you're on campus or near New Paltz, I would greatly encourage it. This is total aside, but you should take advantage of the resources that SUNY New Paltz has to offer by using the Bloomberg terminal. And they have some really good examples of data visualization, as I'm showing here, of just that little line chart next to the difference and changes. And there's this Bloomberg Market Concepts class that is a 10-hour course, and it can provide you just some interactive introduction to financial markets. But back to our class. Another note to mention is the use of small multiples in time series instead of displaying money, deflated, and standardized units of monetary measurements are nearly always better than just nominal units. So showing this change rather than say this is the value. The human intuition of understanding these changes is actually really powerful. And it also diminishes the clutter on a graph. It's easy for the human eye to quickly compare between the values. And the Bloomberg terminal uses this often to show that. So let's go forward. Thinking about this effect size, these are just all of the summary of what we just talked about. So we should think about data to ink, no chart junk, using small multiples, and avoid redundancy in communication. I just wanted to show you some really beautiful graphs too, as we finish this up, thinking about some of the best data visualizations For most data science courses, you might think about what is the first use of data viz, and they usually talk about Jon Snow and the cholera outbreak that happened, where he mapped where the water sources were compared to where there were outbreaks of cholera. And this was one of like the first uses of data science to actually solve a problem in real life, using like data visualization in this case, where you could actually see that near water sources, there was a high amount of cholera outbreaks. So now you could perhaps go and avoid using that well once we have this information visualized one-to-one. But in tabular format, this would have been very difficult insight to derive. On the right is another really beautiful and very kind of well-known visualization of the march between, it's iconic, from Charles Joseph Minard, depiction of the Napoleon March, where in 1812, Napoleon marched to Moscow in order to conquer the city. And it was a disaster. I'm just reading from notes now. I don't know too much about the history, but you can see from this map that they started out with 470,000 soldiers and returned with just 10,000. And this chart tells the story of the battle campaign. And over time, you see the histogram essentially here of like how many soldiers are remaining has diminished over time. And it's just one of the very famous visualization. And similar to the name of the founding Huguenot colonists that started the town of New Paltz, although not related, if you've seen Dubois Street in New Paltz, but W.E.B. Dubois is a different person and very like definitely one of the biggest pioneers in data visualization, especially when it comes to using data visualization to give a highlight on institutional racism in the world. So thinking about how can data information be used to prove a point, to really show a lot of injustice as well in numbers, is really powerful when you can start to use data to actually show what's going on in the world and have it be so visually simple and elegant that it proves your point and people can recognize something like social injustice. And that is the end of our lecture. So next I will go into a Python demo where we walk through how we create some of these different graphics.